I'm excited about the talk today. We're going to cover some of the most fundamental aspects of how to work with data as a software developer, and it relates directly to how computers operate. So it's going to bring together a lot of the concepts we've covered in the first two courses in your education. We're going to cover things here that you'll carry with you throughout the rest of the time you use computers and program computers. So this is a fun one and quite important. What we're going to discuss is the concept of abstract data types. Now, as a reminder, abstract means the theory of how a thing will work instead of the actual implementation of that thing. I'm going to give you a concrete example to kind of help think with this. There's the concept when you're looking at some sort of system or machine of the interface, i.e. the way someone interacts with it, the things it can do, as opposed to the implementation, how the things this machine or system can do are actually done. We're going to use a car as an example. So here we have a car. A thing it can do is turn. The interface that the user sees is a steering wheel. A thing this car can do is accelerate. The interface that the user sees is a gas pedal. It can decelerate. The interface that the user sees is a brake pedal. Now, most people when they use the car don't know how these things work, quote unquote, underneath the hood. Actually, literally under the hood in most cases. What they do know is they know the interface. They know how does it behave, not how do we make that behavior happen. Many people won't know, for example, the different types of physical connections that happen between the steering wheel and the wheels, and literally what physically happens when you turn that wheel. They might not know that often there's a separate pump involved. A motor is called a power steering pump that actually gives you some boost of power so that you don't have to turn the wheel with as much force in your arm. They might not know that. Not that important. They don't really need to know it to operate. For those of us who are car nerds or just like to understand how things work, that's kind of a cool thing to know. They might not know the different physical assemblies that go in between both the left and right front wheels and how they interact and how they both turn at the same time. They don't need to know that to operate the car. All of those are implementation details, how we make the behavior of the car happen. What the user sees is the interface. How does this behave? What happens if I turn the wheel this way? What happens if I turn the wheel that way? What happens if I hit the gas really hard? Don't do that, by the way. What happens if I hit the brake really hard? Also try not to do that. Again, the implementation here, how it actually works, is hidden away. It is abstracted away. And that's a verb you'll hear quite often in this industry. Now, we covered this a bit, but it was way back many videos ago, so I want to reinforce it. We're going to look at that concept as regards different structures of data. Because again, a computer is a data processing machine. And the principles that you'll learn here apply to virtually every aspect of making the computer process data. So let's start to look at actual data types, the concept of an abstract data type. Now, an abstract data type will be the description of a type of data, a specific structure of data, and the description of how it behaves. It does not include how you get it to behave that way, the implementation of the behavior of that data structure. As an example for this, we're going to use a simple array. Here is a one-dimensional array. It is composed of 5 consecutive numbers. And remember, an array has a property called an index. That's what position, generally starting from the left, is an element in the array. There are 5 elements in this array. Their indices, plural of index, indices, are 0, 1, 2, 3, and 4. Good. This is review. But let's look at this. Now, let's discuss behavior for a moment. We have a simple array here. There are a number of operations or actions you might want to take on this array. We're actually going to break out the most common operations you might want to take on this, and then we'll return to the idea of an abstract data type. But for now, we're going to look at this specific array, this simple example, and what are the things you might want to do with that data. So we're going to cover common operations you might do on collections of data. The first two are shown right here. There's a sort and a search. Now, there's going to be a lot more detail on sort, but as a concept, it would be ordering a collection of data according to certain pre-established criteria. let's just assume here that the sort is quite simple. We want these numbers in this array to be ordered in increasing or ascending order. Here is the result. On the top you have the beginning array with indices 0 through 4 and values 5, 2, 1, 7, and 6, now sorted in ascending order. You have values 1, 2, 5, 6, and 7 at indices 0, 1, 2, 3, and 4. You have sorted this collection of data. You can think of similar things by sorting things out alphabetically, that sort of thing. Here's a second common operation on a data structure, a collection of data in a certain structure. Find where we have a value equal to 7. As you scan through here, you'll see we have a value of 7 at position or index number 3. The result is that value is at index of 3. You might also have a search that goes the other way. Find the value that is at index number 4. The result is 6. So those are two common operations applied to data structures. Let's look at a couple more. Two more common operations that can be done on collections of data or data structures. Insert. Here we look at the example on this simple array of adding the value 3 to the end of the array. Here's our beginning array, 5, 2, 1, 7, 6, in indices 0, 1, 2, 3, and 4. And we tack on the value 3 to the end of the array. So we have a sixth element to this array. It has an index of 5, and it has the value 3. Good. Now, there's also remove. Let's take a couple different examples. One, remove where value equals 1. We have our beginning array here, 5, 2, 1, 7, 6. Let's remove the element where the value is equal to 1. The element with the value equal to 1 is right here. It's number 2. We remove it. We're left with 5, 2, 7, 6. Notice that we have only 4 elements. They are numbered 0 through 3. You don't have a jump and skip on what the indices are. These positions are based on the size of the array, the data structure. That's common to almost every programming language. Then there's another example of remove. Remove the index, number 3. We have our array, 5, 2, 1, 7, 6, you're familiar with now, with indices 0, 1, 2, 3, and 4. Well, index of 3 is our value 7. So here's our new modified array, 5, 2, 1, and 6. We've removed the index that was equal to 3. Now we have a new 3, and it has a 6 in it. So those, again, are two more common operations you can do on data structures. Here's another common thing that can be done on a data structure or a collection of data. You can modify one or more elements in that data structure. As an example, let's say we wanted to make any values in this array that were equal to 1 equal to 2. Here's our beginning array, 5, 2, 1, 7, 6, quite familiar with it at this point, with indices 0, 1, 2, 3, and 4. But we apply this, make values of 1 equal to 2, and the value in index 2 now becomes a 2. 5, 2, 2, 7, 6 is our new array. Let's look at one final operation. This final example of a data operation I'm showing you is one of the most valuable. And in fact, the earlier examples wouldn't be possible without this concept. It's the concept of traversing or traveling through a collection of data or a data structure. Let's do an example. Let's say that we've been given the assignment of adding all of the values in this array together. Just what is the sum of all of these values? Now, you and I, we can look at this and do it in our head. 5 and 2 is 7, and 1 is 8, and 7 is 15, and 6 is 21. How do we tell a computer to do that? Well, now we're actually going to look at some actual code. Now, for some of you, this may be your first actual time looking at real code. And this is real code. It happens to be in a language called C# that you'll learn much later in the program. But it's a very, very simple concept. And I think we can get past any of the syntax or form and arrangement of the words here to get at the underlying understanding. And the understanding we're going to arrive at is, what does it mean to traverse or travel through a data structure? So we were given the task of adding all values together. When we look at that, we have an incredible computer, our mind, and we just process it. 5 and 2 and 7, 1 is 8, 7 is 15, 6 is 21. Hey, we're done. We just did a whole lot of things all at once. But here's what we did. in code. The first thing we're going to do is we're going to store the total somewhere. I'm going to make the name of this in red, and what this is a variable. That way we'll be able to see it as we go through the code. It's the most important part of what's happening here, really. So we are making an integer variable. We're calling it sum, and we're initializing it, or giving it an initial value of 0. And to recall, what that means is, somewhere over in the random access memory of your computer, a memory location has been given an identifier, and that identifier is sum, S-U-M, and it's storing a value. That value has been set to 0. That's what's physically happening down inside the computer. But what you do is you write integer, sum is equal to 0. This is the declaration of the variable, sets aside the memory location. This is the initialization, populates the initial value, or sets the initial value. Good. So that's your first line of code. So right here, first line of code. The second line of code is actually several different things. It's everything inside of here. Because what this is a loop. Now, we've covered some of the fundamental elements of any computer program already. This loop is one of the constructs or elements you'll find over and over again throughout computer programs. And it's basically a combination of branching and control statements, but it's designed to allow you to traverse or travel through a data structure and do something to that data structure and its elements as you move through it. Here, what we're doing is we're creating a loop that will let us go through this array and one at a time add up the values in the array so we have a sum. So look at how it works. The green is my comments. It's got nothing to do with the actual code, the actual computer language. We start with this instruction called for. For says, hey, I'm about to have a loop. We're about to repeat a single instruction or multiple instructions over and over again as long as certain conditions are met. Those conditions are given right inside these parentheses. In here, we do three things. The first thing we do is we set up another integer called I. And I'm going to make I in red so it'll be easy to follow. What this integer does is it stores how many times we've been through the loop. We're also going to use it to identify which index of this array am I about to work with, am I about to do something with. So it holds two functions. Let's look at how that works. So first thing here, we're going to break this down. Take your time on this. If you need to pause, rewind this, totally fine. Here's one complete computer instruction right here. You should be quite familiar with this. We just did something like it right here. This is the declaration of a variable called I, and the initialization of that variable to the value 0, just like we did over here. The next instruction is actually a conditional operator. And what it says is, as long as I, which starts at 0, is less than this thing, which tells you how many items there are in the array, how many elements, then keep on doing the loop. Now let's break that down in a little more detail. What this part right here represents is, it's called an expression. The computer can take this and figure out the math on it. What's the math? Well, let's look at our array that we're going to apply this whole thing to, figure out how many elements there are in it. That's called the count. And now we get a number. Here, the number is 5, because there's 1, 2, 3, 4, 5 elements to that array. So let's write over here that array.count is equal to 5. Now, I want to stress something. This code will apply to any array that we want to. We happen to know, because we're using it as an example, that this one has 5 elements in the array. It might have 1. It might have 10 million. It might have none because nothing's been entered into it. We're going to use this example to relate how this code works. But I think you can see this code will work on any size array we tell it to operate on. Because we haven't taken this and just set it to 5. We've said, no, look at the incoming array, figure out how many elements there are. Okay, good. Let's step back a little bit. Because remember, what we're concentrating on is what's happening inside these parentheses. And what's happening is we're setting up the conditions for a loop. That's why it comes right after the for instruction. First thing we did, we set a counter for the loop. We initialized it to 0. Second thing we did, we wrote down under what conditions we will actually execute the instructions in the loop. We're going to execute them as long as this counter variable is less than, in this case, 5. Last thing, each time we do the instructions in the loop, we add 1 to this counter variable. The plus plus is shorthand in this particular computer language that I'm using for add 1 to whatever you were given. It's that syntactic sugar I referred to in an earlier video. It lets you do something very shortly and sweetly that would be a lot harder. You could actually break this down into about 4 different lines where I equals I plus 1. Or you just go I plus plus, and the computer knows it's the same thing. Good. So look what we've done inside these parentheses. We've taken the for instruction. It says, hey, we're about to do a loop. Oh, how does it work? Well, it's all in here. We're going to have a counter for the loop, initialize it to 0. You're going to do the loop as long as that counter is less than, in this case, 5. And every time you've done the loop, you're going to add 1 to that counter. The actual instructions to be executed are right here. It's one line. What this line does is it takes the variable sum, whatever it happens to be equal to when we hit this line, and it adds whatever is in the index of the array that's number I. Now, that may take a moment to sit in or to sink in, because again, for many of you, this is the first time we're really looking at code. So let's break this down a little bit. First, let's start back here. What does this mean? This, again, is an expression. Basically, think of it as math that can be evaluated by the computer. In this case, by the time the computer gets to this little chunk right here of instructions, it will have a value for I. We actually know that the very first time we go through this loop, the value of I is 0. So what this expression means is go to the array, to the index equal to this number, and get the value. In this case, the very first time we go through the loop, this will be equal to 0. In the array that we happen to know about, at index 0 is the value 5. So, the very first time we go through this loop, sum will first be equal to 0, and we're going to make it equal to 0 plus 5. So all of a sudden, sum is equal to 5, which makes sense. Again, this is what you did in your head. You started out with nothing, you got to the first number, you said, well, we're at 5. But then you went on to the next one. What I'm showing you here is how to tell the computer what you just did. So I got marks all over this. Take a look at those, pause if you need to, because we're going to come back to terms like the counter, the conditional statement, the expression. But we're going to go through this with all this noise around it. I'm about to erase this. If you need to write it down, do so. I actually highly recommend that. Okay. We're now going to go through this code one tiny step at a time, and we're going to illustrate the process of adding up all the numbers in the array and how the code actually does that. So, when the computer hits the first statement, it creates a variable called sum. It initializes it to value 0. sum is now equal to 0. We're going to keep track of it down here. We hit the for instruction and we define the parameters of a loop, how the loop's going to operate. The loop is going to have a counter called integer. We set that counter's value to 0 to begin with, so I is 0 down here. We're going to keep on looping through the code inside these brackets as long as this counter, which happens to be 0 right now, is less than the count of the array. We're going to use this array as an example, so the count is 5. Every time we do go through this loop, we're going to increment or add 1 to this counter. So we have now set up the parameters of the loop. We do, in fact, meet the conditions to go through the loop because I is 0, which is less than 5. So we now execute this line. Here, we're setting sum to a new value. We're saying the variable sum, which is currently equal to 0, is going to be equal to 0 plus the value of the item in the array at position I. I is equal to 0. What is the item in the array at position 0? It happens to have a value of 5. So 0 equals 0 plus 5. Sum equals 0 plus 5. Sum, as a variable, has now been given a new value of 5. So let's erase this down here. We have a variable with the variable with the value 5. Now we hit the end of the loop because we're done executing this. There's nothing else to execute. So because we hit the end of the loop and we set up how this loop works, we know the next thing to do is to increment that variable I, which we're using as what's called a counter. So I gets incremented. We add 1 to it. It now equals 1. Good. Next thing to do, check, do we continue to execute the loop? Is I, which is currently equal to 1, still less than the count of the array? Well, the count of the array didn't change. It's still 5 elements, so 1 is definitely less than 5. We're going to do this loop again. But now, when we do it, it's a bit different. Sum is now equal to 5. We're going to make it equal to its current value, 5, plus the value of the item in the array at index 1. Why 1? Because I, which is our counter, happens to be equal to 1 now. What is the value of the item in the index 1 in this array? The value is 2. So sum is equal to 5 plus 2. Sum equals 7. Now, let's write that in, because in the computer, that has now changed inside random access memory. Wherever that memory location is storing the value of the variable called sum, we've changed that to 7. And you can even get a little bit geeky about it and realize, well, in binary, that's, let's see, we got a 4, and we got a 2, and we got a 1. Look at that. That's 7. That happens to be what's inside that memory location. That's just added fun. So we've executed this instruction right here. We've taken our incoming value of sum and made it equal to itself plus the value at the item in the array equal to what this variable I is. Good, we're done. Well, we need to go increment I again. I was 1, we add 1 to it, now it becomes 2. Now we need to check, do we actually continue the loop? Well, I is 2 now. 2 is still definitely less than 5. We're going to do the loop again. All right, let's go back into this. Plug in our new values. We have sum equal to 7. So it becomes equal to 7 plus the item in the array at position I. Position I is 2. What's the item in the array at position 2? It's 1. So 7 equals 7 plus 1 is 8. Let's change that variable sum to the value 8. We're done with that. We hit the end of the loop. We have to increment the counter, the variable I. I was 2. We add 1. Now it becomes 3. Now we check, do we actually do the loop? Well, I is equal to 3. Hey, guess what? 3, still less than 5 in this universe. So we're going to do this item again, or this loop again. So now let's reset these variables. Sum is equal to 8. I is equal to 3. So we're going to set sum to a new value. Its current value plus the value of the item in the array at index 3. That's a 7. 8 and 7 equals 15. Let's change sum to 15. Good. We're done executing the one line we have in our loop. Let's go back up, increment our counter, this variable called I. We're going to add 1 to it. It becomes 4. I think you see where this is going. Here, we're now going to check, do we keep on doing the loop? Well, I is equal to 4. That's still less than the count of the array, 5. So, yeah, we're going to do the loop again. So we go down here. These variables have new values. Let's plug them in. Sum is equal to 15 at this point. I is equal to 4 at this point. So we're going to make sum equal to a different value. Its current value plus the value in the item of the array at index 4. That's a 6. 15 plus 6 is 21. Let's go change the value of that variable to 21. That's what the computer is now storing for it. And we're done with this loop. We go increment. We add 1 to the counter, this variable called I. Add 1 to it. 4 plus 1 equals 5 is now equal to 5. Do we continue the loop? Well, I don't think so. Because I is now equal to 5. And 5 is not less than 5. So we're done with the loop. As soon as we're done with the loop, the computer goes, OK, what's next? What's after this curly bracket? Now, that's in this particular programming language that we happen to use curly brackets to define the instruction or instructions that are part of a loop. As you go through various computer programming languages, it might be a different symbol, but the concept is the same. We have defined where this loop is, where it begins and ends, and once we don't meet the conditions for executing the loop, we go past it and continue on. And that's what we've done. So now we come to a really cool instruction I haven't even talked about, but it's pretty straightforward. We're going to print something on the screen. And we're going to print total is, and then we're going to put the value of sum, the variable sum at that point. So on your screen, it will say total is 21. And that's a computer program. But what this is an example of is traversing through a data structure. We have started, in this case, at index 0 of an array, and we have gone through each ascending item in that array. An array is an example of a data structure. And we've done something with either the array or the items in it or an external sum variable. In other words, we've been able to move through this data structure and perform data operations. That's what computers are all about. Now, we've covered about 6 or 7 fundamental things that you can do on data structures. I'm going to list those out now and make another point to come back around to the idea of abstract data structures. Okay, so on the left here you see these 6 common operations you can apply to data structures. Again, sort, move all the data elements around into a new arrangement. Search, find one or more elements inside that data structure. Try to find something that you were trying to match inside the data structure. Insert, add something to the data structure. Remove, take something away from the data structure. Modify, change one or more elements inside that data structure. And traverse, move through some or all of the data structure, presumably so you can perform a data operation. Now, I mentioned a moment ago that this traverse applied to virtually all of these other ones, and I think you can see why. If you're going to sort through an array, for example, you're going to have to go through it a number of times in order to reorder it, say, in ascending order, which was the example we used for sort. You're going to traverse it. You're probably going to traverse that array many times to put it into ascending order, for example, to sort it. Search, you're going to have to traverse at least until you find what matches on a search. Insert, you might not need to traverse. But what if you actually want to insert something at a certain point inside that order or arrangement of the data structure? You'd have to traverse to a certain extent. Modify, well, you'd have to find the item that you actually want to change. That can involve traversing through the data structure until you find it. And, of course, there's traverse, which is itself a thing you can do with the data structure. You're usually doing it to perform one of these other things to the data in the data structure or to the structure of the data itself. Good. Now let's come back to the concept of abstract data types. There is an abstract data type of an array. And this abstract data type of an array, and let's just say it's a simple array, which will be a list of data elements in order, is going to have some sort of behavior. Some of the behaviors that you could expect an array to have are these right here. You should be able to sort and search and insert and remove and modify and traverse an array. But the implementation of those behaviors is not part of the abstract definition or understanding of an array. It's a specific choice, usually by a computer programmer, on how to do that behavior. And the example we just produced in code a few moments ago is an example of implementation. We were given the task, please go through this array and add up the sum of all the values in the elements of the array. The way we chose to do it, or rather I did and you looked at and learned, is I decided to use the indices starting at 0 and moving up to the end and add up the values in each one. Well, let me ask you a question. Couldn't we have started at the last one and moved backwards to the beginning? We would have gotten the same total. 6 plus 7 is 13, and 1 is 14, and 2 is 16, and 5 is 21. We could have. That's our choice as to how we implement the behavior that's asked for. The person who's consuming or using this array and its behavior of traverse and add up the sum doesn't need to know how we implement it. And this is one of the central aspects of computers and computer programming, is separating out the abstract idea of how a behavior will be or a data structure will be formed from how that is actually done, how it's implemented. Because I just showed you there's two different ways just to perform the data request or the data operation we were asked to do. And there's actually a multitude of ways to solve virtually any computing problem you're given. How you solve it is a question of implementation. What it's supposed to do, how it behaves, is a function of the interface into that data structure. And you will come back to this concept over and over and over again. I want to make a particular point about being a junior developer, being someone who's new to this industry. This is one of the central things you'll bump into as you go out into the job market, is that very often you'll be given the task, hey, produce some code that does the following. What they're telling you is the behavior they expect. They aren't necessarily saying to you, listen, we need you to figure out the absolute most efficient, best way to do this for the exact business case we have, and it's got to be perfect and gorgeous and look like someone who's been to college for 39 million years did it. All they're saying is, here's the behavior we want. Solve it. Often when you do so and you get it working, what you've given to the senior developers is a working example of code that implements a specific behavior. Now they can take that code and they can change it all around to make it faster, more efficient, more applicable to the types of data that are seen at that company, but they have a working implementation to deal with, and that's incredibly valuable. And as long as you recognize the fact that you've implemented the behavior, and it may not be in the best way possible, but you've got something to work with, you start to recognize your value as a software developer. But it also brings the flip side of it. If someone else discovers or recommends what is honestly a better implementation, sometimes you have to let go of the fact that, well, it does what it's supposed to, and I built it, and I like my code. Highly recommend, just in terms of sanity as a software developer or a technology professional, being willing to waste, scrap, unload, get rid of any code you've ever written. Just get rid of it. If there's a better way to do it, latch onto that, learn it, figure out why it was in that specific situation that it was a better way to do it. But it all starts with understanding the behavior that's expected and how you implement it are two completely separate things. And that's where the concept of abstract data types comes in. An abstract data type of an array will simply define the structure of the data and the behavior you expect out of it. It will not define how you implement that behavior, how you make it occur. Now we're going to apply that principle of abstract data type definition versus implementation to two of the most common data structures you'll find in computing. We're going to look at the abstract data type of a stack and a queue. These are going to be defined by the way the data is structured and the behavior of the data structure, what it can do. This is going to center around two concepts you'll find very often in computer science. First in, last out, and last in, first out. And they define a behavior of a data structure. How you implement it, that enters the realm of implementation, not abstract. So we're just going to look at the abstract behavior first of a stack and then of a queue. And it relate to these concepts of first in, last out, and last in, first out. First, a stack. Okay, so let's look at the concept of a data structure called a stack. A stack is simply a stack of data that is in ascending order by when it was inserted into the stack. The oldest items are at the bottom, the newest items are at the top. Some examples might be a stack of plates at a cafeteria. You have all the plates, they're in a well. When you grab a plate, what you're grabbing is the last one that was added to the stack. But this is a stack of plates. And by the way, what I just referred to gets into a little bit of the behavior of a stack, which we'll discuss in a moment. Here's another example. We could have a list of numbers. The first number that we were given is 5.7, then we're given 2.3, then 9.7, then 42.0. This is a stack of those numbers. The top of the stack contains the most recently added number. Now, this is the structure of the data. Items arranged in ascending order of creation or addition to the data structure. That's a stack. Good. Now, what's the behavior? The behavior involves how we get data from the stack. And the behavior is a last in, first out behavior. The way a stack works is if you put a new item in, it goes on the top. And if you go to retrieve an item, it comes off of the top. It was the last thing added to the stack. I think one of the best ways to illustrate this is the example of the undo and redo buttons that are common to very high number of computer programs. We're all used to this in, say, a word processing program. You can actually undo your recent edits to the program, or you can redo them. That computer program, say Microsoft Word, actually has a stack data structure. In the stack is, one after the other, all of the words you've entered in to that document. And when you do undo, it goes to the most recent word you typed and removes it from the document. You can hit undo again. It will remove the next most recent word that you added to the document, and so on and so forth. And if you changed your mind and did the redo button, it would still be keeping track of it because the programmers are doing their job, and it would put them back into the page in that reverse order. So here we have the abstract concept of a stack of data arranged in ascending order based on when that data was added to the collection, and with a behavior definition of last in, first out. Other behavior definitions could be called push. Push means adding an item to the top of the stack. Or could be pop. That means removing an item from the stack, and again it comes off of the top. It could also be an is empty operation. Essentially, are there any more items in the stack? These are all examples of descriptions of behavior without implementation. We don't know, for example, how exactly the code is written in Microsoft Word that keeps track of the thing I just talked about with the undo and redo. But we know the behavior to expect from it. And that's all we need to know as consumers of the product. The programmers, on the other hand, would probably be tasked with getting the most efficient and best way to implement that behavior. That's not part of an abstract data type. The description of what you want that data structure to be able to do is. How you implement that behavior, that's implementation, and again, that's where software developers come in. Now let's look at another data structure, very similar, called a queue. So this is another abstract definition for a data type. It'll involve the structure of the data and some of the behavior. So it's called a queue. Queue, by the way, is a very common term in the British world, and it means a line. So that'll probably make sense as we go through this. The structure of the data is like this. It is a consecutive series of data elements, but they are ordered in descending order based on when they were put into the actual data structure. The way they work is on a first in, first out basis. The first item that's put into this data structure, if you want to retrieve something from the data structure, is the first one you put in. So if these were numbers, we used some examples before. If you went to retrieve a number from this queue, you'd get the 2.3 first, because it was the first thing put in. Once it's gone, the next one available, which in this case is 4.6, love my handwriting, I'm sure, becomes available. So here you have a structure defined and some of the behavior, first in, last out. The other things, of course, that would apply are same thing, push, which means adding something to the data structure. It would go in on the tail end, not on the top, it goes on the back. So you have a sixth item, let's say it's 9.6. Pop, that's to take one off. First in, first out. The one you take off is going to be the oldest one in the stack, the one that's first put in there that still exists. You could also, of course, have an operation called isEmpty. Is there anything in the queue? So an example of this would be the line at the ticket gate when you go to an airport. Everybody lines up in order, and they're going to take the first person they got in line, and they're going to process them. That person's gone. They're going to process the next person, and so on until there's nobody left on the line. So to relay this all back to the concept of abstract data types, how we implement a push or a pop or checking isEmpty, those things are not detailed here. The behavior expected is detailed, and all that detail comprises the definition of an abstract data type. This type of data type is called a queue. There is one other behavior to mention, and it applies to both a stack and a queue, and that behavior is peek. All this means is check the value of the next item that would come out of this data structure if I were to actually retrieve it. In this case, in a queue, that would be looking here at, oh, it's 4.6. They haven't removed it, but if they were going to, that's what it would be equal to. Now, that points out a pretty interesting thing. There's a difference between seeing what's in the data structure and modifying that data structure by removing elements from it or processing things in it. Most of the time, you're going to actually grab something from a data structure, do something to it, you're done with it, so you discard it, and then you move on to the next item in the data structure. But not always. And this is where actions like traverse come in valuably. But again, that's a description of behavior. How you implement it, how you implement that, well, that's implementation. It's not part of the definition of this data type. So you have a lot of data there in this video. We covered concepts related to just the abstract definition of a data type or data structure versus the actual implementation of some of that structure and behavior. We actually looked at real code. I highly recommend that if you didn't follow every single little bit of that, you go back and look through that code again. It should be very educational if you've never done any coding before. And finally, we looked at a couple of very specific examples of abstract data types, the stack and the queue, and these will apply all the way through your software development career.